Wireless, untethered communications encircle our globe and reach beyond our universe into deepest space. Today, communications technology advances at an unprecedented rate, constantly challenging us to unleash its full potential. Wireless communications is a global industry that people depend on in countless ways. For effectiveness in business, for efficiency in service, for situations where clear, unhindered communications may mean the difference between life or death. This is an industry that grew in just over 50 years into a multi-billion-dollar enterprise. As we approach the 21st century, this is an industry in the forefront of technology, where tomorrow, communications throughout the world will improve in ways in which we can now only dream. So let your imagination soar and join us for a look into the exciting world of wireless communications.
Hello, and welcome to the Fundamentals of Radio Communications, a program which explores one of the most important and dynamic industries of our time, wireless communications. Two-way radio touches the lives of virtually everyone, no matter who they are or what they do. It's a lifeline in emergencies, a convenience when in need of service, a necessity for improving organizational productivity. And for those of us who work in the industry, it's something more. It's our business, an exciting, challenging, and competitive business. If we're going to work and succeed in this business, it's essential that we have a basic understanding of two-way radio, what it is, how it works, why it's important. That is the mission of this program. Now, it's appropriate that we begin here at the Motorola Museum, a showplace that not only captures the legacy of the past, but also looks ahead into the seemingly limitless future of radio communications. When it began, some called it a revolutionary breakthrough. Others dismissed it as a mere novelty. Few grasped its potential, and absolutely no one envisioned this technology as someday creating a global industry indispensable to the public safety, transportation, manufacturing, utilities, media, retail sales, businesses of every category and in every market of the world. Perhaps, though, these early users should have anticipated this explosive growth. After all, it's driven by people's basic need to communicate and exchange information with one another. And it's been that way since the very beginning. Here, face-to-face communication worked just fine, since everyone spent a lot of time huddled around a fire looking at one another. But as mankind increased in numbers and migrated throughout the earth, communication got harder. How do you speak with someone you can't see or hear? So people turned to various devices: drums, smoke, flags, runners, riders, and wires. Each made their mark. Each improved communications. Each advanced society another rung or two up the ladder of civilization. But the real breakthrough did not occur until the late 1890s. That's when Marconi used electrical signals radiating into space to achieve the first wireless communications. This started a revolution, and things haven't been the same ever since. What made this happen? How did it work? Well, let's take a look.
When a stone is thrown into a pond, the energy propelling it produces waves which radiate out from the source of entry in a series of concentric rings. A similar phenomenon occurs when alternating electrical current travels along a wire. Only here, the resultant waves are electromagnetic in nature. In radio, an antenna functions as one very large wire to radiate these electromagnetic signals. But to first produce these signals, a transmitter must oscillate or move the electricity back and forth at a rapid rate. This back and forth movement of electricity generates the electromagnetic signal radiated from the antenna. That's not all. The transmitter also amplifies the signal, giving it sufficient strength to send it out from the antenna and into space. This amplification is similar to using greater force or throwing a larger stone into the pond. The added energy transfer causes the waves to move further across the water. If the waves pass an object in the water, such as a branch or leaf, the object moves in concert with the waves. So it is whenever a transmitted electromagnetic signal passes a receiving antenna. This signal or wave induces a small electrical current which moves back and forth along the antenna in time with the oscillations of the electromagnetic wave. Although this current is much weaker than the one in the transmitting antenna, the receiving antenna can pick it up. Then, by means of circuitry in the receiver, it amplifies that signal. The rate a radio signal moves back and forth is called its frequency. It's measured in hertz. One complete cycle of oscillation equates to 1 hertz. Most radio frequencies have millions of cycles, or megahertz per second. Radio waves of seemingly endless frequencies fill the air around us. An antenna picks up these frequencies indiscriminately. In order to listen to one frequency, something else is needed. Each radio has a means of selecting a narrow band of frequencies at any one time. It acts much like a funnel with a filter, allowing only certain size elements to pass through. In this case, it's a specific frequency. This filtering process occurs whenever someone tunes a radio to listen to a specific radio station. And if they don't like the music there, they can move up or down the dial to another frequency and another song. This ability to tune a radio to a certain frequency range enables someone to respond to radio signals meant specifically for them.
Radio communication best serves people on the move. Now, while there are lots of reasons why such people need to communicate with one another, these intentions fall into 2 broad categories: economic and safety. The economic reasons include all the ways to use two-way radio in business to cut costs, increase profitability, improve customer service, or just gain an edge, a competitive advantage that makes the difference. When it comes to safety, there are several reasons for two-way radio: to improve the ability to respond to emergency situations, to enhance personal safety by maintaining contact with people in potentially dangerous situations. But whether the reason is economic or safety, the fact is that radio gives people better control. Control over the resources they manage, control over the events about them. With this as background, let's take a few minutes to learn how radio actually works.
For wireless communications to occur between 2 points, a simple radio system requires a few fundamental components, namely, a transmitter to send the message and a receiver to pick it up. At the transmitter, a microphone converts the sound of the spoken message into an equivalent electrical signal. Because this signal is weak and delivered in a low audio frequency, it cannot travel very far. So the transmitter processes and amplifies the audio signal, combines it with a radio signal, and delivers it to the antenna. The antenna radiates the radio signal containing the voice message into the air. At the other end of this simple system, a receiver reverses the procedure. The receiving antenna detects the radio signal and sends it on to the receiver, which processes and returns it to an audio signal. This sends it to a speaker, transforming the signal to its original form, audible sound waves, heard just as they were spoken. This system allows a person at one site, such as an office building, to communicate with another person, perhaps riding in a vehicle located many miles away. The process of combining an audio signal with a radio signal is called modulation. In this process, the message or voice signal is impressed on a radio frequency, or RF signal. We call this the RF carrier since it literally carries the message along as it moves through space. While a voice message usually modulates the carrier, tone signals or digital information may also be used. In this manner, radio transmissions are used to communicate data. There are 2 basic types of modulation: amplitude modulation, known as AM, and frequency modulation, or FM. Amplitude modulation is typically used by commercial broadcast stations and in citizens band radio. AM is susceptible to noise and static interference. Television, high-fidelity broadcast radio stations, and virtually all two-way radio systems use frequency modulation, since FM signals are far less susceptible to noise.
Of course, there's more to modulation than just AM and FM. Why, some of the state-of-the-art systems of today, like digital, incorporate other modulation techniques. But that's for another time. For our purposes, let's focus on FM. Okay, now we have the big picture of a two-way radio system. Let's take a closer look at the basic components that make up that system.
Two-way radio equipment can be placed into three categories: fixed, mobile, or portable. Fixed equipment refers to the radio equipment positioned at a central site like an office or headquarters, where a manager or dispatcher maintains control by communicating to a field force. The radio equipment at such a site is called a base station. A base station includes a transmitter, receiver, power supply, and typically has a built-in speaker. A standard power source from a wall socket usually powers the equipment. A base station requires a microphone and antenna and includes all necessary controls which usually appear on the front panel. These include the on-off power switch and volume control. Depending on the types of options available on the radio, there may be additional controls as well. There are three types of base station control configurations to consider depending on the location of the antenna site. These are local control, extended local control, and remote control. A local control base station is used when the dispatch position is close to the antenna site. Here, the entire radio unit usually sits on the dispatcher's desk. Extended local control may be used in situations where the dispatch point is up to 1,000 feet from the antenna. In these situations, the antenna site houses the transmitter, receiver, and radio power supply sections, while the radio's controls reside in a separate unit at the dispatcher's position. A wireline cable connects the two. A remote control configuration is required when more than 1,000 feet separates the antenna site from the dispatch position. In this instance, it may be necessary to use wireline, or at least telephone lines, to connect the radio's transmitter and receiver with the control unit at the dispatch point. A remote control module is added to the base unit to interface with the wire lines. A base station can have more than one remote control unit, allowing it to be controlled by different people from several locations, such as shipping, expediting, and management. While the base station or fixed equipment forms the communication hub, its spokes radiate to the mobiles and portables in the field. A mobile is a two-way radio installed in a vehicle. Its power comes from that vehicle's battery. Most mobile radios are compact enough to mount under or near the dash. In some applications, the mobile's transmitter and receiver mount in the trunk. A small control head attached to the dash contains the radio's controls. The control head connects to the main radio unit with cables. An external speaker is also available for mounting under the dash. A portable radio is a unit small enough for a person to carry on the job. A portable radio gets its power from a self-contained battery. The portable unit comes complete with a transmitter, receiver, built-in speaker, microphone, and an antenna attached to the top.
Base stations, mobiles, portables, as you can see, two-way radios come in a variety of shapes and sizes. They have varying capabilities depending on the sophistication of the equipment and the option selected. Now that we've seen a two-way radio system and its basic components, it's time to learn how they operate.
In a basic two-way radio system, a microphone converts a voice message into an audio signal, which is sent to a transmitter. By a process known as modulation, the transmitter combines the audio signal from the microphone with a high-frequency radio signal. This is called a carrier, since it carries or transports the voice signal. The modulated carrier signal is sent to the antenna, which in turn radiates it for reception by other radios. The receiving radio's antennas detect a portion of the radiated carrier. The antenna sends this modulated carrier to the receiver, which demodulates or removes the audio signal from the carrier. It then moves to the speaker, which transforms the electrical signal into audible sound. If the receiving radio user wishes to respond to the message, the process reverses. This basic two-way configuration describes a single-frequency simplex system. It is the simplest form of radio communications. A simplex system consists of two or more radio units operating on a single frequency. Both the transmitter and the receiver share the same frequency. One unit may be a base station. One or more may be mobiles or portables. Because every unit transmits and receives on the same frequency, users cannot talk and listen simultaneously. Simplex means transmission in only one direction at a time. We can equate a simplex operation to two trains traveling in opposite directions while sharing the same section of track. The eastbound train must wait until the westbound train passes. The eastbound train can then be switched onto the common section of track and proceed. If both trains were on the track at the same time, they would collide. This is true when transmitting and receiving in a simplex system. Two-frequency simplex is another type of radio system. In this system, the transmitters operate on one frequency while the receivers operate on another. This is used when the dispatcher must maintain system control. In such a case, the base station transmits on frequency 1 and the mobiles receive on frequency 1. Likewise, the mobile transmits on frequency 2 and the base station receives on frequency 2. The mobile units cannot talk to or hear each other because their receivers operate on a different frequency than their transmitters. The dispatcher is the only person who can hear all traffic. A radio repeater is yet another system. This is a special type of base station remotely located from the system's base of operations. The repeater consists of a transmitter and receiver, just as any base station. However, it operates a little differently. When the repeater receives a signal from the base station or a mobile unit, it immediately retransmits or repeats that signal. In this fashion, it acts as a relay. The repeater operation is called duplex because it can receive and transmit at the same time, much as when someone talks on the telephone. Properly located on a high building, tower, or mountaintop, a radio repeater will increase the operating range of the communication system. In addition, a repeater can put a radio signal into what would otherwise be dead spots, normally inaccessible with a typical two-way radio system. A radio repeater is an excellent way for extending a system's range and improving mobile-to-mobile, portable-to-portable, or base-to-mobile and portable communications. The most common type of repeater system relays messages between mobile or portable units. Here, the mobile transmitters operate on one frequency and the mobile receivers operate on another. The repeater transmitter operates on the mobile unit's receiver frequency. When the repeater receives a signal from a mobile, its transmitter turns on and retransmits the message, typically at a higher power and from a better vantage point than the mobile's originating transmission. In this system, all mobiles and portables communicate through the repeater. In some systems, the radio unit has an additional frequency that switches to transmit on the receiver's frequency. This permits mobile-to-mobile or portable-to-portable communications and allows radio units to talk with one another when they are out of range of the repeater. This is called repeater talk-around.
Basically, that's how two-way radio moves messages from here to there to just about everywhere. Of course, ideally, radios would receive only those messages they need to hear. Unfortunately, receivers hear the transmissions of everyone else who is on the same frequency and transmitting within range. They also hear any noise that may be present in the radio's signal. While nothing can be done to prevent the receiver from hearing this, it doesn't mean that the listener has to hear it. By adding special electronic circuitry to the radio's receiver, it's possible to reduce or squelch unwanted signals before they are heard in the speaker. There are two basic types of squelch, carrier squelch and coded squelch. Take a look.
Carrier or noise-compensated squelch prevents hearing noise in the speaker when there are no transmissions occurring. This is an example of such background noise. We can eliminate this by adding a squelch circuit in the receiver. On some radios, a squelch control allows the user to adjust the squelch setting level to cut out this background noise. In most radios today, an automatic squelch circuit replaces the manual control. The proper squelch level is set automatically as needed. Another type of squelch, called tone-coded squelch, has special circuitry which allows listeners to hear only those messages intended for them. Like carrier squelch, a coded squelch receiver picks up all messages transmitted on its frequency. However, with coded squelch, the speaker only opens after receiving the message with a pre-assigned code. Coded squelch requires circuitry in both the transmitter and the receiver. Just as voice modulates onto the RF carrier, a coded squelch signal is also modulated and transmitted. At the other end, the receiver demodulates the voice and coded squelch signals. A decoder in the receiver examines the demodulated squelch code while comparing it to its own built-in pre-assigned code. If the codes match, the speaker opens, releasing the message for someone to hear. You can think of coded squelch as a sort of combination lock. After entering the proper code or combination, the lock opens the speaker, giving access to the message. An incoming signal on the same frequency with a different code or no code at all will not open the speaker. The lock remains shut. The message goes unheard. The two most common types of coded squelch are tone-coded squelch, called private line or PL, and digital coded squelch, called digital private line or DPL. It is important to remember that even though coded squelch users hear only messages with their specific codes, in this case code 02, and do not hear other transmissions on the same frequency, those signals are still present. While coded squelch systems eliminate the annoyance of listening to other transmissions, they do not ensure privacy. Each radio has a switch that defeats the coded squelch circuit. This is necessary since users must listen to make certain no one else is on the channel before transmitting. Otherwise, this could disrupt a transmission already in progress.
Well, we've covered a great deal in this introduction. Basic system configuration, modulation, equipment classification, simplex, duplex, repeaters, squelch. These are the building blocks for getting a solid foundation in understanding two-way radio. There's more, though. Lots more to discover about this fascinating field. As I said in the beginning, this is a vibrant and dynamic industry that's growing all the time, and if we're going to play an active part in it, then we need to grow as well. So join me next for segment 2, where we'll learn about antennas, towers, and transmission lines. See you then. Antennas. They come in different shapes and different sizes. Welcome back to our presentation on the fundamentals of radio communications. In this segment, we're going to find out more about the role antennas play in determining with whom we can communicate. We'll spend some time reviewing antenna classifications and characteristics, the towers they're often mounted to, even the transmission lines connecting them to transmitters and receivers. As you'll see, they all work together to make radio communication possible. Ready?
An antenna is a device designed to transfer radio signals from a transmitter and radiate them into the atmosphere. While a number of factors go into determining just how far these signals travel, the antenna is one of the most important. We call the geographic area over which a radiated radio signal travels the coverage area. This coverage area is very important to users who want the radio system to communicate with their field personnel no matter where they're located in the territory. Antenna systems help define the shape and extent of this coverage area. An omnidirectional antenna radiates a radio signal in a 360-degree pattern. With this antenna, the range extends out about the same distance in all directions. Omnidirectional antennas are used when it's possible to place the antenna at or near the center of the coverage area. For example, if an organization's county-wide base of operations is located somewhere in the middle of the county, an omnidirectional antenna would deliver full coverage throughout the area to meet the communication requirements best. However, different organizations have different requirements, different geographical areas in which they work. It is often desirable to alter an antenna's radiation pattern by making it more directional to suit the customer's specific coverage needs. There are three types of directional antennas: cardioid, unidirectional, and bidirectional. Gain is a characteristic of directional antennas. Gain refers to the antenna's ability to increase its effective radiated power, thereby expanding the normal coverage area. Antennas that focus or concentrate radiated signal coverage in one direction send out a stronger signal in that direction. As a result, signal strength increases or gains in the direction of the concentration. At the same time, there is a corresponding loss in signal strength in all other directions. Cardioid antennas are appropriate when an antenna site is near the edge of the coverage area. The cardioid antenna gets its name from the heart-shaped radiation pattern it produces. This antenna concentrates signal strength in a single, albeit broad, direction to increase the maximum range. This concentration of energy toward one direction results in reduced coverage in the opposite direction. Cardioid antennas tend to reject radio signals received from the opposite direction. This diminishes the amount of potential interference and unwanted signals on the user's system. A cardioid antenna functions well in a situation where a natural barrier, such as a lake or mountain range, does not permit full use of a radio system. A unidirectional antenna generates an even more focused radiation pattern, aiming the radio signal in a narrow band. When a geographical strip or corridor requires coverage, a unidirectional antenna works best. For example, when the requirement consists of point-to-point communications with a remote repeater site, a unidirectional antenna is a likely answer. A bidirectional radiation pattern can also be generated. Bidirectional antennas increase coverage in the directions perpendicular to the plane of the antenna, such as might occur on a long strip of highway or along a railroad right-of-way. As demonstrated, there is no one right antenna or antenna pattern. A radio system must be designed to suit each organization's own requirements for coverage, direction, and distance. A thorough survey of the organization's operation, along with the geographic terrain in which it functions, will yield the information needed to recommend the proper antenna system.
As you can see, in order to have an effective communication system, the antenna location and characteristics must satisfy the specific coverage requirements. But that's not all. There are other factors to consider, factors like antenna height and base station power.
Towers often raise antennas to a height necessary to cover a required geographical area with radio signals. Antennas also may gain needed elevation by mounting them on buildings or by placing them on top of a hill or mountain. Given their height, government regulations may require special painting and lighting for towers to avoid presenting a hazard to aircraft. The government may also require customers to notify certain agencies of any proposed tower construction and secure all appropriate licenses and permits. Because of the sizable investment needed to secure a site and erect the structure, towers frequently support several different antenna systems. In addition to tower location and height, one more factor contributes to coverage range: base station power. A base station is usually located as close to the antenna site as possible. A transmission line carries radio signals between the base station and its antenna. This line is made of outer and inner conductors called coaxial cables. Attenuation, or signal loss, is one of the most important design considerations in using transmission lines. All transmission lines dissipate some power which diminishes the original signal strength. The longer the cable length or smaller its diameter, the larger the signal loss. Because of attenuation, the transmission line length determines the diameter necessary. The longer the length, the larger the diameter required to maintain signal strength. To illustrate this, consider a pipe through which a large number of balls must travel. Because of friction with the walls and the bouncing of one against one another, energy is expended. Not all get through to the other side. This means that there is less energy delivered at the end of the pipe than at the beginning. However, by increasing the pipe's diameter, the balls have an easier time passing through it. Therefore, more make it to the end of this pipe to deliver more energy than did with the smaller one. The same physics apply in a transmission line. Here, the objects passing through are electrons, not balls. This means that the further the base station is from the antenna site, the larger the transmission cable diameter needed to minimize signal loss.
There are a number of factors that affect radio signals and the coverage area: antenna type, height, location, the transmission line connecting the antenna to the base station. All these are extremely important elements in designing a radio system. But there are other considerations as well, and we'll examine them next in segment 3 when we look at frequency and spectrum. I hope you'll join us. Radio signals. What are they? How do they differ from one another, from other forms of energy? Well, we're about to find out as we examine frequency and spectrum. In this segment, we'll review radio waves and their frequency characteristics. We'll also take a look at the frequency bands where radio systems operate and consider how to select the right frequency band to match operating requirements. So, what is frequency? Quite simply, it's the measurement of electromagnetic waves, waves which surround us, from the sound of my voice to the light of this exhibit.
As you've seen, the radio frequency signal radiated from the antenna begins in the transmitter's electronic circuits. In order for the signal to break away from the antenna to become a radio wave, the transmitter must drive the signal back and forth at a very high speed. In measuring signals, we refer to each complete back and forth movement as a cycle. Frequency is simply the rate of movement or oscillation. In other words, the number of cycles per second. If a signal moves back and forth at a rate of 1,000 times per second, it has a frequency of 1,000 cycles per second. To simplify things, we substitute the term hertz for cycles per second. So in this example, the frequency would be 1,000 hertz. Two-way radio signals occur in a range of millions of cycles per second. Again, for simplification, we refer to this as megahertz and abbreviate it as MHz. You'll encounter other terms in examining frequencies. For example, kilohertz, which is 1,000 hertz, and gigahertz, or 1 billion hertz. The electromagnetic spectrum is the total range of frequencies of electromagnetic radiation. It extends from the lowest audio waves to the highest light waves. For example, the light that allows you to see this videotape belongs to the electromagnetic spectrum occurring between 600,000 gigahertz and 900,000 gigahertz. Audio frequencies reside at the low end of the spectrum and range from 15 to 15,000 hertz, or 15 kilohertz. Most people hear the frequencies in this audio range. Voice signals, for instance, fall between 15 hertz and 3,000 hertz. Because the electromagnetic spectrum goes from a low of 15 hertz all the way up to several gigahertz, or billions of cycles per second, we divide the spectrum into more manageable segments called bands. The frequency bands pertinent to radio are VHF low band at 25 to 50 megahertz, VHF high band from 136 to 174 megahertz, UHF from 403 to 512 megahertz, and the 800 and 900 megahertz bands. Each frequency band has certain distinct characteristics. This is true of both radio and light waves. Light has several obvious ones. We know, for example, that light travels in a straight line, that an obstruction can shadow it, that certain surfaces, such as glass or water, reflect it. But other characteristics are not as evident. Water vapor and dust in the atmosphere absorb or attenuate light. Consider the headlights on an approaching vehicle. You can see them better on a cold night when the humidity is low than on a foggy one, because fog diffuses light. Refraction is another characteristic. Refraction takes place when light moves from one medium to another, which alters the light ray's direction. Look how a straw in a glass of water appears bent. That's refraction, a characteristic of light. Radio signals have similar characteristics. The atmosphere surrounding Earth acts to attenuate and refract radio signals just as it does light. The frequency determines how great the effect. As a guideline, the lower the frequency, the less the attenuation or loss of signal. Thus, lower frequency radio waves penetrate fog or dust better than higher frequency ones. Here's another example. Low frequency AM broadcast radio signals travel far beyond the horizon and can reflect back to Earth to be heard hundreds of miles away. By contrast, the Earth's atmosphere absorbs higher frequency television or FM commercial broadcast signals. This limits their range to line-of-sight transmission. The opposite occurs below 300 kilohertz, the other end of the spectrum. Here, radio waves follow the curvature of the Earth for great distances. We call this form of propagation a ground wave. By making use of low-frequency ground waves, it's possible to have radio communications over the span of several thousand miles. We find a unique characteristic when we move up the spectrum to the frequency band from 300 kilohertz to about 30 megahertz. When they're sent with enough power in the proper direction, the ionosphere will sometimes reflect and/or refract the radio signals in this band. As they return to Earth, they are received hundreds or even thousands of miles away from the point of origination. We call this characteristic skip and use the term sky waves to label the radio signals having this reflective property. The most suitable frequencies for two-way radio transmission generally fall between 30 megahertz to about 900 megahertz. Line-of-sight propagation characterizes radio frequencies in this range.
So far, we've given you an overview of some frequency characteristics, sort of a mini class in basic physics. Because of natural phenomena and differing radio frequencies characteristics, specific frequency bands are usually assigned to certain applications or uses. For example, lower frequencies are used for worldwide communications because they follow the curvature of the Earth and are not as easily dissipated by atmospheric conditions. Let's explore this a little further and see the influence frequencies have on radio system design. After all, VHF, UHF, 800 and 900 megahertz bands each have distinct characteristics that may be advantages or disadvantages to radio users.
Machines, engines, and other devices generate electromagnetic noise interference as a byproduct of their activity. These can be troublesome to radio reception. Because such noise occurs in the lower frequency ranges, VHF low-band signals are very susceptible to this type of interference. VHF high-band signals, by comparison, have minimal susceptibility to noise interference, while UHF and 800-900 megahertz signals have virtually none. Obviously, low band is not a good choice when operating in a high noise area. Next, consider range characteristics. In rural areas, VHF low-band signals have the best range. Their low frequencies tend to follow the curvature of the Earth for long distances. While not the equal of low band, the range characteristics for VHF high band in this setting are also good. The UHF band and 800-900 megahertz bands have only fair characteristics for range. Foliage and terrain common to rural areas attenuate signals in these frequency bands. From this, we can see that the VHF bands offer the best choices for rural areas. The situation is a little different when considering suburban areas. Here, VHF low-band signals have the good range characteristics. VHF high-band signals have excellent ones. The UHF band rates a good, while the range characteristics for 800-900 megahertz bands is only fair. Radio in urban areas differs dramatically. The range for VHF low-band signals is quite poor here since they cannot penetrate the many buildings. Noise interference is high in these areas, which affects low-band signals. VHF high-band signals work better, having good range characteristics. The UHF band and 800-900 megahertz bands are better still. Because their signals bounce off of and penetrate buildings, they have excellent urban range characteristics. From this comparison, you can see that low band is not a good choice for use in urban locations. Selecting a frequency band requires making many compromises. There are two general rules to aid in decision-making. First, as the frequency increases, range decreases, but so does the ambient electrical noise. Second, reflections from buildings increase with frequency. By following these general rules, we can say that low-band VHF is generally more suited for large rural areas. High-band VHF for suburban and those mixed urban-rural areas. With UHF and 800-900 megahertz bands most suited for pure urban applications. Each of these radio frequency bands is further divided into many sub-bands. These are assigned to users depending on the type of operation or application. For example, mobile cellular users in the United States are assigned to frequencies in the 824 to 849 megahertz range.
Since frequency spectrum is a finite resource and the number of users in many areas is extremely high, radio channels may be congested. This is the result of channel loading, the term that describes the number of users assigned to the same frequency. Channel loading is so prevalent in some areas that additional users are excluded from certain channels or frequencies. Government agencies in most countries authorize and license channel use. In the United States, the Federal Communications Commission, or FCC, is charged with regulating communications, including two-way radio, television, wire, satellite, and cable. International regulations fall under the jurisdiction of the International Telecommunications Union, or ITU. In all cases, the law requires a license issued from the appropriate governing body in order to operate two-way radio equipment. That license grants permission to communicate on a particular frequency or frequencies and defines certain eligibility rules users must meet. Spectrum management and conservation is a global issue. Not only are government agencies using regulations to help conserve and manage our spectrum, they're also encouraging the adoption of new technologies that have the potential to make our use of the spectrum more efficient. Many of these technologies are available today, and we'll take a closer look at some of them in later segments. The purpose of a radio system is to deliver communications over a distance. But what distance? How far? To where? Key questions to consider when designing a two-way radio system. This segment gives some considerations to those questions. Considerations needed to optimize the radio system range and coverage. During the next few minutes, we'll examine those factors having the greatest impact on range and coverage. Factors like the radio's frequency band, transmitter power, antenna type, height, and location, the surrounding terrain, and the amount of electromagnetic noise in the area. Let's look at each of these in a little more detail.
The first step in selecting a frequency band is to determine where the radio system will be used. For example, assume a user wants to talk from a base station to a mobile radio. If the user is located in a medium-sized community of, say, 100,000 to 200,000 people and desires coverage over a portion of the city along with the surrounding suburban area, chances are a VHF high band frequency, if available, meets the requirements best. If the user desires coverage of the downtown area of a larger city and has a high antenna site, such as a tall building available, UHF is the appropriate band to select. The reason? Radio waves in the UHF frequencies radiate effectively in and around tall buildings. By contrast, if the user operates in a rural area and wants coverage throughout a large portion of that area, a VHF low band is their best choice. The factors affecting frequency band selection include the availability of antenna sites, future expansion of the area, the electromagnetic noise environment, and, of course, frequency availability. After selecting the frequency band, it is time to consider the antenna. Antennas radiate energy in all directions, much like a light bulb radiates light. A mobile radio moving away from the transmitting antenna receives less radiated energy as the separation distance increases. The distance from the antenna to the furthest point communications can take place is known as a radio system's range. As a radio moves away from the base antenna, signal strength weakens. At some point, the signal is too weak for reception. Conversely, the mobile cannot generate enough energy from its own antenna to reach the base station. When this occurs, that radio has reached the limits of its range. If you think of range as the radius of a circle, the circle itself defines the coverage area. When drawn on a map, This circle indicates the radio system's usable area. Many different factors affect coverage. Base station antenna height and location are the most critical, since a radio system's range is theoretically limited to the horizon as seen by the antenna. Basically, the higher an antenna rises above the ground, the greater the coverage area. Because the radio waves follow a line-of-sight path, terrain variations can impede communications. Hills and valleys create shadows or communication holes in the coverage area. Tall buildings may have the same effect. In these cases, raising the antenna height eliminates most of the hole. Antenna height, to a large extent, solves terrain problems. Location is also important. For example, selecting a 3,000-foot hill for an antenna site serves little purpose if it's surrounded by 5,000-foot mountains. The necessity for avoiding noisy locations is less obvious. Noise, of course, refers to electrical interference of any type, caused, for example, by nearby power lines, neon signs, electric motors, or other radio systems.
There's no denying noise does affect radio system coverage. Did you ever have someone turn a vacuum cleaner on in another part of the house while watching television? If so, you might have noticed that the vacuum cleaner motor generates electrical noise, reducing clarity of the television signal. Well, that type of noise is a problem, a potentially major one for radio coverage. Is there anything we can do? Sure. The answer is intelligent system design.
As a radio moves away from the base station antenna, it eventually receives too little energy for effective communications reception. Noise problems at these limits of the coverage area, called fringe areas, can be severe. The radio signal is simply too weak compared to the noise signal. In fringe areas, increasing transmitter power can increase the energy level at the receiving radio's antenna and help to overcome the noise. Gain antennas offer another way to overcome this problem. Keep in mind that gain represents an antenna's ability to increase its effective radiated power. This is accomplished by channeling the antenna's normal radiation pattern in a particular direction, thereby extending the distance covered. Using a high-gain antenna ensures better reception in the system's fringe areas.
As you can see, many factors affect range and coverage, and as experience will show you, there are always trade-offs and compromises in designing any type of two-way communication system. When putting that design together, always keep in mind this one overriding point. The most desirable two-way radio system you can create will meet the customer's specific communications requirements for the lowest cost. Enough said. We'll see you in the next segment. Welcome back as we continue to explore the fundamentals of radio communications. Throughout this program, you've heard the expression radio systems used again and again. But what are they? How do they work? When is one better than another? It's time to find out. In this segment, we're going to review radio systems, and we'll cover three different classifications: conventional, trunked, and paging systems. The majority of radio systems in use today are conventional systems. For many users, they deliver the best combination of functionality and cost effectiveness. Now, within the broad classification of conventional systems, there are several specific types to consider. These include unit-to-unit, central dispatch, and the repeater systems. Let's begin with the unit-to-unit system.
Unit-to-unit is the most basic type of conventional system. This system allows field personnel to communicate directly with each other. Unit-to-unit systems equip users with two-way radios, either mobile or portable, giving each person the capability to both talk and listen. However, because these radios transmit and receive on the same frequency, a user cannot talk and listen simultaneously. Regardless of the number of radios in the system, only one radio user can talk at a time. A central dispatch system is another type of conventional radio system. Here, a communications link forms between a central dispatcher and radio users in the field. When the dispatcher wants to call one or more field units, he or she transmits the message over the radio system. Everyone with radios tuned to the same frequency hears the message from the dispatcher. Likewise, field personnel can initiate a conversation or respond to the dispatcher. A repeater system constitutes yet another type of conventional system. You may recall that a repeater is a special form of base station. When the repeater receives a radio signal, it immediately retransmits that signal. Since the repeater has much higher transmitter output than a mobile or portable, a repeater is an excellent way to extend the coverage range.
Many people who need and use radio communications cannot afford or justify the cost of their own repeater system. Well, in these cases, a community repeater bears looking into. After all, it is one way to acquire the benefits of a repeater system without incurring all the associated expense. As the name implies, a community repeater is a repeater system shared by many users. Here is an example.
A community repeater system is strategically located in a suburban area. Joe's Plumbing and Al's Limo Service share the repeater and antenna as a service instead of each owning their own repeater. Both companies do have a central dispatch control station and mobile radio units in their respective vehicles. This allows Joe to talk with his plumbers as they travel in their trucks from job to job, and Al to dispatch his limo drivers when customers call in for pickups to and from the airport.
Conventional radio systems are the foundation of the two-way radio industry. They deliver cost-effective, reliable wireless communications to millions of people every day. However, this widespread usage creates a potential downside. While most metropolitan areas have a high number of radio users, there's only a finite number of available frequencies. This gives rise to the problem of frequency congestion. And just like the overcrowded highways during rush hour, this congestion often means delays, frustrations, and inefficiencies. This problem has led to a great deal of effort to develop spectrum conservation techniques to ease congestion. Trunking systems is one of the results of that effort. Simply put, trunking efficiently meets the communication needs of a large number of users by sharing a small number of communication paths. This example will explain the process.
We can equate a trunked radio system to the way modern telephone companies deliver service to their subscribers. Note that individual phones are connected only to a switching station. When a caller wants to make a phone call, a temporary line referred to as a trunk is assigned. After dialing a number, the opposite end of the trunk automatically connects to the receiving phone. Since the two parties have exclusive use of the assigned trunk, they can talk without other parties hearing them. In addition, other people have the freedom to make their own calls through different assigned trunks. When the first two callers finish, the trunk assigned to them becomes available for additional calls.
Just as this analogy depicts, trunking improves calling efficiency. The most obvious benefit is its ability to minimize waiting times that delay and confound users. But users of Motorola's trunking technology enjoy even more benefits. Since it's software-driven, Motorola trunking has a number of user and system management capabilities not available on other types of radio systems. See for yourself.
A Motorola trunked radio system begins with a series of repeaters. While this system shows 5 repeaters, it is possible for a trunk system to have up to 28. One of these repeaters is assigned the duty of transmitting and receiving data information. This repeater is designated the control channel. In this illustration, the control channel is repeater number 1. All others function as voice channels. Connected to the repeaters is a central controller, a computer that acts much like a traffic cop. It processes all inbound and outbound data. When receiving a request for a voice channel, it assigns an available repeater. A trunked system divides users into groups. Each user group may